In this video, we're going to be covering related rates focusing on a rectangle and multiple different parts of a rectangle changing, okay? So what I'm going to go ahead and do is I'm going to go ahead and read this question, identify all the pieces that are uniform throughout each part. The width of the rectangle is decreasing at a rate of 3 centimeters per second. So I'm going to go ahead and draw myself a rectangle, and we're going to go ahead and talk about the width. Now, it doesn't matter which one you label as which. I'm going to call this one width just because I'm used to calling the base the width. Okay, now that means that off to the side here I have W equals, I'm going to have length equals, I'm going to have dW dt, and it says the width of the rectangle is decreasing. And again, let's recall, when I say I'm decreasing on a length, my rate is 3 centimeters per second, but it ends up being a negative 3 centimeters per second. Okay, while the length of the same rectangle, so this length right here, is increasing at a rate of 2 centimeters per second. So my dL dt is equal to a positive 2 centimeters per second. Again, notice negative, decreasing, positive is increasing. When the length is 12, so I'm going to go and write that down, length is 12, and the width is 5. Okay, so now they actually filled in all of this information. Let me go ahead and look at the first part of the question. What is the rate of change of the rectangle's diagonal? Okay, so if this is length and this is width, my diagonal cuts through here. Okay, we can call that whatever we want to. In this case, I'm going to go ahead and start by labeling it as a C value. Okay, so in part A, they want to know, again, what is the rate of change of the rectangle's diagonal. So I'm going to go ahead and draw myself a line here. This is all uniform information throughout the entire problem. Part A, I need what is dC dt equal to. Well, chances are, if I'm looking for dC dt, I might need to know what C is as well. So let me go ahead and identify an equation that relates L, W, and C, those lengths specifically. Well, if you look up here, they did give us a bunch of these formulas. Which one of these formulas will satisfy the relationship between the length, the width, and the diagonal? Well, you'll notice that this right here is a triangle that relates those three lengths. So it's not going to be area, it's not going to be perimeter, it's going to be this Pythagorean theorem, again, a squared plus b squared equals c squared. So this is the equation that I'm going to be using on this one. But in this case, I'm going to go ahead and write down, instead of a squared plus b squared equals c squared, I'm going to write down L squared plus w squared equals to c squared. And remember, I'm going to go ahead and take the derivative of all this. But if you've recalled the previous triangle problems we've done before, you'll notice that, again, I'm going to have to take the derivative of all this stuff. But when I do, very carefully, I'm going to have 2 times L dL dt plus 2 times W dW dt equals 2 times C dC dt. And again, that's because the derivative of L squared is 2 times L. Don't forget, we're taking the derivative of all these pieces in respect to t. So this is our derivative. Again, if you're having issues with this, please look back to, I believe, video 3. Now, in this situation, I have L dL dt, W dW dt, and I'm looking for dC dt, so that should be unknown. But notice I don't have my C value. So I'm going to have to go ahead and find C. In this case, I'll be plugging in what W and L are into this formula and solving for C. So L is 12 squared plus W is 5 squared, and this is equal to C squared. When I go to solve this equation, I'm going to have 144 plus 25, which is 169, and C squared equaling 169 gives me that C is plus or minus 13, but again, we're talking about lengths here, so it's 13 centimeters. Okay, so again, I'm going to square root both sides of this equation, and the square root of 169 is 13. So I now have the C value. I've been given all of this information. I'm going to plug all of this information into here, providing me with 2 times 12, the length of L. Okay, let me scroll this down so you can see both at the same time. 2 times L, dL dt is 2 centimeters, so I'm going to go ahead and plug in 2, plus 2 times W is 5. Let me plug that in. dW dt is negative 3 equals, and then I'm going to have I'm going to have 2 times C, 2, and my C value is 13, times dC dt, which is what we're looking for. So I'm going to leave that as unknown in the problem. So now we have a simple equation with dC dt being the only variable. So over here I'm going to have 48. Looks like minus 3 times 2 is 6 times 5 is 30. equals to, looks like 26 dc dt. This is going to provide me with the value of 18 divided by 26 equals dc dt, where I can simplify just a little bit and get dc dt is equal to 9 over 13. And now let's recall what the unit's supposed to be on this. Well, c is in terms of centimeters, my time unit is in terms of seconds, and again I'm going to check that one more time in terms of this problem. It is centimeters per second, so that means this makes sense to be centimeters per second. So this should be the value that we're looking for. Let's just verify that this makes sense. Okay, now verifying that this one makes sense might be a little bit more complicated than the previous ones. Keep in mind the width is decreasing at a rate, so this is going to get smaller. Okay, the length, however, is increasing at a rate, so this is going to get longer. So this makes sense for it to be almost changing in a positive or a negative sense. Okay, it almost makes sense for it to be changing in a positive or a negative sense. So it's possible that this could be still wrong, but I'm going to go ahead with our gut that we've done all of this work correct and that this should make sense. So that there is part A. If we'll continue reading, part B follows what is the rate of change of the rectangle's perimeter. So now we're looking at dp dt, where again they gave it to us. The perimeter is 2 times L plus, that should be a plus sign. Again, the perimeter is 2L plus 2W. So I'm going to go ahead and flip this page over or get myself a new piece so that I can continue to use the same information in the beginning of the problem. This all was given and is standard. Okay, and again I'm looking for what is the rate of change of the perimeter of that rectangle. So recall the perimeter is equal to all the sides added up, L plus W plus L plus W, which is 2L plus 2W. And this problem I think is going to be a lot easier than part A, because in this problem if I take the derivative of all sides, again d dt of P and d dt of this side, I'm going to end up with dp dt equals the derivative of 2 times anything is just 2 times, and then the derivative of L is dl dt, plus the derivative of 2w is 2 times dw dt. And you'll notice in this problem we don't need to find anything else for us to find dp dt. So again, in this case, dp dt is going to be equal to me plugging all the information in. 2 times dl dt is 2 plus 2 times dw dt is this negative 3. In that case I'm going to have 4 minus 6, which is a negative 2. So this is the perimeter changing. The length of the perimeter is going to be changing at negative 2. Negative 2 what? Well, perimeter is a singular powered unit, so centimeters seems to work for that. Okay, it's not an area. Area would be covering everything inside here, and that unit would be squared. But since we're just covering the length outside of it, it's centimeters, and then again per second. So dp dt is a negative 2 centimeters per second. Finally, we're asked what is the rate of change of the rectangle's area? In which case, again, we're still looking for a rate of change, but in this case we're also looking for the rate of change of the area. So we're going to need to have this A equals length times width, the area of a rectangle, which is this formula here. So when I'm looking at this, the area of the rectangle is length times width, which if we're going to take the derivative of this, again, to find, again, what is the derivative of A in respect to t, I need to take the derivative of length times width. But the problem with this is, keep in mind, this is length times width, which is a product. And therefore, when I'm taking the derivative of 2 different variables in terms of a multiplication, I'm going to have to apply the product rule. In which case, this is going to be my f, and this is going to be my g. Okay, so L is f and g is w. So in this derivative, we're going to go ahead and take the derivative of the first, which the derivative of L in respect to t is dl dt times, leaving the second function unchanged, times w, plus the derivative of the second function, which is the derivative of w, so dw dt, times, leaving the first unchanged, L. In which case I now have a formula for what is dA dt when I have dL dt times w plus dW dt times L, which you'll notice up here again we have all of those values already identified. So if I plug all that information in, dL dt is going to be 2 centimeters per second, in which case I'm just going to write 2, Our W is going to be 5 centimeters, so times 5, plus dW dt is a negative 3, and then finally L is 12. By plugging all that information in, we'll identify that this is 10 plus a negative 36, and therefore a negative 26. The problem, however, is that we need to again have the unit on this. Keep in mind that this is an area measure, and therefore a change in area. Given that it's the change in area, and area is a unit squared measurement, we're going to end up having centimeters squared per second. And again, it's per second because it is a rate. So in that case, we now have dAdt, finally, in terms of our final answer, as negative 26 centimeters squared per second. And that finishes all three of those parts.